Vocabulary. The next thing we're looking at, the vertical line test. It's a test of a graph to see if it represents a function. Because as we discussed earlier, every domain only leads to one range value, right? So the domains are x. When we look at an x, for example, let's say that this is -2. This is x equals -2. When you put in -2, you should only get one value back. If you get two values back, if we put in 4 into this function, or into this whatever this relationship is, and then we get two values back, then that must mean this is not a function. Same thing here. If we draw a line through it and we intersect more than one point, then it does not represent a function. This is the vertical line test. Okie dokie. Remember when? Recall that an equation is a representation of a relation. Equations can also represent functions. Right? This should not come as a surprise because I've already been doing it for things like where y equals x plus 2. This is an equation that represents a function. Every solution of the equation is represented by a point on a graph, so we could graph this out. In fact, we could probably just use the whole graph. So if x is 0, y is 2. If x is -2, y is 0. If x is 2, then y is 4. And so that's the function that's graphed out. So the graph of an equation is a set of all of its solutions. So if you look at the graph, it represents all the solutions, and it goes in both directions. It can be a curve or a line. To be honest, though, most functions in real life do not end up being linear, which is a line or a curve like this, or something else. Usually it's some other thing going on, because in real life things are usually not as neat as just being a simple curve or a simple line. For example, let's go back to the mountain bike thing. Can we write an equation from this situation? Well, there's a rental fee of $125. That means if we rent the bike and then we don't even use it, we just return it, it's $125. For every hour, we add $250 per hour. $250 per hour is like adding $250 every hour, right? Just like I was doing earlier. And we can just keep doing that in perpetuity, forever. We can rent it forever. So adding 250 over and over again is just like multiplying, right? So for example, if you add 250 4 times, or let's even just do 3 times to save time, then that's the same thing as 250 times 3, right? And so I don't know why I erased that. So if we're going to multiply 250 for every hour, then the number of hours that we rent the bike, we can state as a variable, right? And in this case, we're going to call it x, because this is the independent variable. The number of hours that we rent the bike does not depend on the total cost, right? Y is going to be the total cost. The total cost is going to depend on how long we rent it for. So we multiply the number of hours that we rent the bike by 250, and that's going to give us our total cost. And then if we're going to graph this at 1 hour, it would be, what did we say earlier? 375. And then at 2 hours, it was 6 something, right? 625, I think, if I remember correctly. And we're not going to keep, I don't even want to do that. Got ahead of myself. I don't want to keep doing this, but it's going to just be dots here like this. For every hour, we're going to have another dot. It's going to be another 250 more than the previous dot. So that's how we graph and write an equation. Oh, I have a free page here for me to do that. I didn't even need it. More vocabulary. Okay. Function notation is a form of a function where the range is represented by an f of x. That's how we read this, f of x. So instead of saying y equals 2x plus 1, we would write f of x equals 2x plus 1. This is function notation. A linear function, or I'm sorry, a nonlinear function is a function with a graph that is not a straight line. Line, not a line function. Let's look at some examples, shall we? Oh, I feel like I'm flying through this. This is not going to be 25 minutes at all. Unless it is. Maybe I'll slow down. A mountain biking club charges this much money, right? So let's write an equation in function notation. So we had written this earlier, so I'm just going to write it again. It was 125 plus 250x, right? 250x plus 125. So f of 2 is basically saying, what if we put 2 into the x? What if our input is 2? Then we would just put 250 times 2 plus 125. So f of 2 is equal to 500 plus 125. F of 2 equals 625. There you have it. This is written in function notation. This is basically saying that if I put a domain value of 2 in, then this is the range value. Oh, I just drew through that. If the domain value is 2, this is the range value. Let's do it again for an f of x of 6. F of 6 equals 250 times 6 plus 125. Excuse me. 6 times 250 is 1,500 plus 125. F of 6 equals 1625. It's another $1,000 to rent another 4 hours. That makes sense. Yeah. So this is how we write a function in function notation. Same problem. If you rented a bike for 3 hours and your best friend rented a bike for 4 hours, how much would that cost? Well, this would basically be f of 3 plus f of 4. So if you see a problem that asks you this, then what it's asking you to do is find the y values, the range values if your domain was 3 and your domain was 4. I'll just write this up here one last time. I think this is the last time, just for anyone who skipped ahead to this part and they're a little bit lost. Okay, so f of 3 equals 250 times 3 plus 125. Now instead of writing the f of 3 over and over again, I'm just going to write an equals here. So that's 750 plus 125. 875. And then f of 4 equals 250 times 4 plus 125. That's going to be 1,000 plus 125, 1125. And then we just add these two figures together. I don't have much space left here. I'll just do it right here in the middle, I guess. 875 plus 1125. Oh, look at that. $2,000 exactly. Sounds like a good time. Let's take a look at this function here. The figures show a store display. So this is a display that you can use to put things in, I suppose. It's a bunch of shelves at different heights. And this carpenter is someone who works with wood, makes this for local stores. Depending on the height that a store would like its display, the carpenter needs different amounts of boxes, right? depending on the height, right? We would need different amounts of boxes. So if you look at the sentence carefully, you should probably be able to tell which is the dependent variable and which is the independent variable, right? The customer is going to tell this carpenter how tall they want their display, right? So this does not depend on anything. This is the independent variable. The height is independent. So that means the number of boxes depends on, the number of feet. Hi. Graph the relation between the display height and the number of boxes. Okay, so, look at that. Let me just get rid of this stuff. All right. So we can see here that at 1 foot, at the number of boxes is going to just be 1, right? At 2 feet, the number of boxes is going to be 4. At 3 feet, the number of boxes is going to be 9. Some of you might be able to see now the pattern emerging here. At 4 boxes, I could draw this out if I wanted to, right? But I'm not going to. I'm just going to write 16 here because I can see the pattern already. If we put this box here, it makes a square. This is also a square. This is also a square. And then if we put these boxes here and here, we have a square, right? So no matter how high it is, we're just going to continue having squares. And so 5 is going to be 25, so on and so forth. Let's just work with these first ones here. What do we have to do again? I should probably put the instructions on the next slide. Graph the relation. Okay. So if we were to graph this out, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 4. Oh, I don't want to do that. Why did I do that? See, this is the problem with this, is that because I'm not doing this in front of you, no one is here to stop me from doing stupid stuff. I just have to know myself. So this is the number of feet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. At 1 foot, it's 1 box. At 2 feet, it's 4 boxes. At 3 feet, it's 9 boxes. You might be able to tell here that this is not a line. It's actually a curve. Oh my goodness. And it's going to go up faster and faster. This is called exponential. That's because the equation for this is y equals x squared, or f of x equals x squared. In function notation, this is not a linear equation. This is an exponential equation, which means our graph is exponential. I believe that's it. Yeah, it is it. My goodness. Oh, it was 25 minutes. My goodness. Well, I guess I won't waste any of your time. Any more of your time. Bye.